Hi, hello everyone. My name is Jiayang Liu. I'm from University of Electronic Science and Technology of China, and it's my honor to introduce our work to you here. The name of the sharing work is Unsupervised Cross-Domain Image Retrieval with Semantic-Attended Mixture of Experts. And the development of multimedia technology has led to an explosion growth of data on the internet. Due to the differences in acquisition methods, this data often exhibits significant distribution disparities, making mutual retrieval between them challenging. Therefore, cross-domain image retrieval has been proposed to address the difficulty of mutual retrieval between images in different domains. Furthermore, due to the challenge and the high costs associated with obtaining data labels, a more realistic task named unsupervised cross-domain image retrieval has showed up. So as you can see, our setting is in the unsupervised manner, and which means we have not the label or the corresponding relationship between images. We can see the Wang in the picture. The Wang in sketch and the Wang in cartoon have not the label and the corresponding relationship. That means no cross-domain pairing information or category label information available during model training. And as shown in the fig, the giraffes from 4 different domains in the picture. You can see the sketch, the cartoon, the real, and the other domain. And they possess distinctive semantic-related features such as slender legs, unique stripes, and long legs. When the model can correctly capture these semantic-related features, instead of different categories, instance of different categories can be easily distinguished based on differences in these features. Moreover, based on differences in these features, since these semantic-related features are domain invariant, cross-domain alignment can also be easily addressed. So our goal is to capture the domain invariant features. As you can see, different domains have the same features, such as the legs, the necks, and the stripes in the picture, in the fig. And we know that mixture of experts is often used in the field of neural language processing. And nowadays, large language model is very popular. And MOE is often used in large language model. So many large models now utilize the MOE architecture, and researchers using MOE frequently regard it as an architecture capable of handling different types of data. And in recent years, there has also been work applying MOE architecture in the visual domain. And this inspired us to consider that in the unsupervised cross-domain image retrieval task, if each expert can recognize a domain invariant type of visual attribute, our task could be well addressed, much like the giraffe example shown previously. So we hope that each expert can handle the unique type of features, just as the picture shows. This is a typical illustration of MOE in the feed. And to enable the model to fully attend to semantics in an unsupervised setting, and to ensure that the MOE structure equitably recognizes semantics to achieve high-level semantic recognition, we place the MOE architecture in the last two layers of vision transformer. Additionally, we design methods to maximize the model's semantic-attended capability. This is an illustration of our SA-MOE model, and it consists of a feature extractor and a multi-layer perceptron. The feature extractor is employed to map data from two domains to a common feature space. And in the left is our model architecture, and in the right is our loss design. And I will show you the details in the I will show you the details. And the first is semantic-attended data fusion. And as we know, first we introduced semantic data fusion to maximize the extraction of domain invariant visual semantics. We make full use of vision transformer structure. We start by averaging the attention maps of each layer and then applying the weighted attention to the original images, as shown in the fig on the right. And next, we merge two images from different domains, just as the fig shows. The house in the right are in the real domain, and the house in the left is in the real domain, and the house in the right is in the cartoon domain. And we start by averaging the attention maps of each layer and then applying the weighted attention to the original images. Next, we merge two images from different domains, and that might belong to the same category after weighting them. And the model is then trained with pseudo-labels obtained from clustering. And in the right is the visualization of the images after semantic-attended data fusion. And you can see after our semantic data fusion, the semantic in the picture can be highly attention. You can see in the picture. And if we just use random data fusion, the semantic is not visualized. And this is our formalized term. And the second part is contextual semantic association maximization. And we train the model with constructive learning, including instance discrimination and clustering, contrastive learning to learn semantics. And however, simple intra-domain and intra-class contrastive learning can only help the model to make a rough judgment of the semantics based on the distance between instances. To obtain precise semantics, we use contextual semantic association to train the model. And we can use this contextual semantic association as a criterion to select images from different domains that are more likely to belong to the same category. Okay, this is the second part. And this is our experimental results of our model. And we can see that our method achieves the SOTA performance across various scenarios. And besides, we observe greater improvements in abstract domains and noisy domains with significant noise, such as the quick draw and the infograph. And this indicates that our strategy of maximizing semantic enhances semantic learning, making our model less susceptible to noise interference. And now we present our experimental analysis of the model, and we conduct an investigation into the positioning of MOE within the model architecture. And the associated parameters in table, we can see the positioning in the architecture, the MOE positioning in the vision transformer, the every two and the last two, and we compare it with the original vision transformer architecture. We can see that we use less parameters but which achieve greater performance. And this is our ablation study. And this is our visual comparison of attention map between this ICCV work and our work. And we can see that the attention map is much better than theirs. And this is my presentation, and thank you for listening.